Perfect, thank you. Anyone else have an exam? Alexis, can I get your U90 number?
I didn't want to look at it.
Same with these two. Can I have student ID numbers?
You're blonde. I know.
Very sad. Why?
Yeah.
Dodgers were eliminated in the first round after winning one game. Embarrassment of the year. Yeah, really poor.
Really bad.
Y'all had a bad weekend and I had a bad weekend.
You had a better weekend. That's.
Did you have the best weekend? Because you loved the exams so much.
Oh, no. I didn't even.
You learned so much.
Didn't even look at it.
You didn't even look at it
No.
until this morning. An hour ago. Yeah. Makes sense. It was what? That was you, an hour ago?
No.
Okay.
And then we tried to circle each of them. I don't want to put most.
Yeah. Oh yeah, I didn't even check that on here. I guess we'll find out.
I want to put these.
On all of them? Make all of them worth half.
Even middle. Yeah. Middle.
Anyone else have the exam? Remember to put your student ID number here. Thank you. Anyone else? Unbelievable. And you want to name him. Okay, anyone else? Okay. Okay, yeah.
For sure.
Okay. Is that it? Okay. I guess I'll just leave it out here, right? So for this week, we're gonna have two events that you're welcome to come to. One of which is the open house on Thursday night. So this is for the public. Obviously, you're welcome to come to. And then there's a homecoming event on Saturday. I don't know if you need tickets for that, but it'll be sort of the same thing. So if you want to come to either one, that's totally fine. Remember that you get credit for going to these. So easy way to increase your grade. How did that exam feel? Wow, that was a lot of man. Okay, not good. Hopefully the, middlemost least made sense. Did anyone struggle with that? For every question, say question 7 or question 3. Yeah, cool. For every question, there's 3 parts more or less, A, B, and C, and you assign only 1 to each of those. So if you wrote least on the entire exam, I'll just hand it back to you and say, can you fix this, please? Okay. Questions? I won't go over the exam until I've graded it, because if I see like common issues, for example, I might end up giving people credit for that. Right? Okay. So today we're going to talk about the Jovian planets. This is actually a really small chapter in the book, and we've already done some of it. So we talked in particular about, say, ice geology, kind of a weird thing to think about. But we'll come back to that in more detail. Today, we're going to talk about the atmospheres. It's mostly pretty pictures. Just like stop learning things as hard. And then we'll do a little bit of rings in this day. We'll look at some of the other moons that have atmospheres. Weird to think about. And then we'll talk about small bodies. So these will be asteroids, comets, etc. We'll have a whole time for Pluto. Maybe a week, we'll see. Comets are here, that might happen earlier. We'll talk about collisions, which are the sort of break the rules for planetary formation. And we'll talk about how the solar system formed. That's this section and this section. We may or may not move to exoplanets. We have these extra days, 3 extra days. I always like to do a class on the history of everything to put it into context. What order did things happen in? So that can happen in any one of these 3 days. Basically, on one of these 2 days, I'll basically see how much content we have left, how many free classes we have, and I'll ask you for your major topics. So if you got to the end of the class and you're like, I've never learned about blank, that's when you would tell me, and I would fill it in either one of these 3 days. Does that seem like that's okay? That stuff would not make it onto the final. So just be for fun. Okay, because class is learning, but it's fine. Right? Okay. Question before we go on? All right. Okay, so as promised, it's pretty picture day. Yay! No more learning. Okay, so what's this? Jupiter. Good. And what part of Jupiter is this? Great red spot. Yeah, good. And so, of course, the detail here looks like an oil painting. It's real. This is an actual picture. And in fact, we'll see even better pictures than this. Sort of stupid to think about. Anything else you see here? What's that? It looks like gas, right? It looks like clouds. Did anyone do the milk thing with the soap? You're all like taking the exam. You're like, what the fuck is that? So I mentioned this last time. This is like an experiment you do with kids. Sometimes you do it with friends who are maybe indulging in adult circumstances. You put a thing of milk down, plate, but whole milk. Don't use 2%. You want fat in that milk. You can even use cream. Then you drop little pieces of food coloring. And you take a tiny amount of soap, you touch it, and the surface tension will draw all of those colors around the milk. And that's sort of what's happening here. The reason that you see different colors here is that there's different gases. So for example, the color of this gas is orange and red because of the hydrogen that's found in ammonia. And then these parts here are white, and they're very similar to what we have here on Earth. That's water ice. So there's water ice clouds and ammonia clouds, and they give Jupiter its famous color. Okay, Questions about this? You also see this like stormy stuff here. It's really cool. This is two different pictures. On the right hand side, this is a picture of Jupiter in the visible. This is from Hubble, the space telescope. And the one on the left is from JWST. That's correct. You might have seen this at the beginning of the semester. They put this out. So this is a picture in the infrared. Okay. It's not in the visible. And actually what you can see here, a little surprising, is what does infrared light tell us about? How hot something is. Okay. So brighter infrared areas are going to be hotter. And that's actually what you see here. Here at the bottom, it's very bright. What's happening up there is what's happening on the right-hand side. You have particles from the sun that are smashing into the atmosphere. We call them northern lights here on Earth, or aurora borealis. The same thing's happening on Jupiter, just massive. Recall that this is the size of the Earth. So this is many times larger than the Earth. And this is a heating source. So this is material from the sun traveling at high speeds and smashing into the top of the atmosphere. Okay? What does that mean with these different pieces here? Which one's hotter, the white or the dark? Right here, white? I just said that myself. Okay, yes. In fact, these are the hotter pieces. And so you say, wait, the great red spot, that's in white. That's really weird. It turns out that's exactly what's happening. Here, this is ammonium coming up from underneath, going up because hot goes up. And as it goes up, it starts to spin. Because remember, Jupiter is spinning at about 11 hours. It makes one full rotation. This massive object is spinning really rapidly. And as it goes up, turns this upwelling, stuff coming up from below, starts rapidly rotating. Okay? So these pictures are in fact related. Questions about that? Okay. Here's some more pictures. So that's that same picture, but now you can see more of it. So you see the aurora on the top here. There's more aurora on the bottom. You can see Io's footprint. We talked about the fact that if you're on Io, there are volcanoes, but there's no atmosphere. And that's because the atmosphere of Io is immediately being dragged off of the planet and smashing in to the top of the atmosphere, Jupiter's atmosphere. If you look to the left, you'll see, oh, it's really hard to see in here, but I promise they exist. Little tiny bitty rings. Okay, we'll talk more about rings. Of course, the largest rings in the solar system are Saturn, right? That one's the easy one. And you might be thinking to yourself, okay, well, here's this weird little star thing. Here's another star thing. In fact, those are not stars. Those are moons. So Jupiter has lots of them. Jupiter has like 60 or 70 moons. We talked about 4. Those are called the Galilean satellites. The first one is over on the left of this picture. You can't see it in this picture. It's quite bright. It's very large. It's called Io. And there are ones that are smaller. You can see that here. This is Amalthea. And this 6-sided shape is, of course, the signature of JWST. You'll also see like these ones coming off here. That's just diffraction. That's when scattered light is distorted in the telescope. So it doesn't mean that there's actually a disk coming off the bottom here. Okay. Questions?
Is that like a southern aurora? Oh, yeah, it is.
Yep. Perfect. Here's another example. Should we turn the lights off for this, or are we going to fall asleep? Definitely turn them off, right? Who cares? All right. You did the exam. Everyone turn the exam in?
Yeah.
Okay, cool. All right, let's go back actually, so you can see the rings better here. And now do they look better? Yeah. Okay. So what happened? Wait, what just happened? Was that a joke? All right, whatever. Okay. So those are the rings. Guess it doesn't look better. And then here's a picture of Jupiter. Come on. So this is not from JWST. It's not from Hubble. This is from a spacecraft called Juno. And Juno is really cool. Juno is around orbit. It's around Jupiter. It's in orbit right now. And it does this really cool thing where it starts out really far away. So this is Jupiter. Starts way out here. And then it comes in like a comet, gets very close, and then goes back out. And it turns out that that process of going in very close can help to change the orbit. So we just use a little bit of fuel at the top, and we can look at the entire planet. So this is a real image. It's stupid, but it looks amazing, right? So as you fly over this thing, and I'll show you a video later, but these pictures are real, and the colors that you see are quite real. Again, noting that this stuff is usually ammonia. Of course, when you get this close, there's a combination of different types of gases. So we'll see some stuff in here that's like phosphorus gas. We'll see some stuff that's water ice. That's normal. And you'll think to yourself, well, okay, all of these clouds are made of stuff that maybe we don't normally think of these giants as being made of. Phosphorus. I don't even know what that is, right? Okay, here's another example. It's a close-up on the Great Red Spot. See anything interesting here? Wish I could want those off, but I don't want it to be too dark. There we go. Is that better or no?
Yes.
Okay. All right. Anything you see here? Yeah. Yeah, it's going counterclockwise. Good. Yeah, you actually can't see the surface here. And we'll talk about what's weird about these ones is there is no surface. So all of these features that you see here are features in the clouds themselves. Anything else you see? Yeah.
It's in the middle, it's more of a deeper red, while on the outer, it's more of an orange.
Yeah. So there's huge color gradient here. So this is very deep in red, as you mentioned. And then all of this material, we talked about it moving around, there's even a small spiral in here. That there are storms within the storms. And maybe that's a theme that we see over and over, right? Here we see it rolling over. All of these places where you see that the clouds are bending back on themselves. These are locations where you have differences between the fluid and they're spinning up, just like you see an eddy or a whirlpool in a stream. Okay. Here's another example. This is the South Pole. This fucking blew my mind on this guy. Okay. What is this? Okay. So this is the south rotational axis of the planet. And what you see here are tons of these circles. What are those circles? Yeah, essentially. That's exactly what they are. There, of course, it's a little weird to think about it this way because the whole atmosphere is clouds. So when I say it's a storm, you're thinking to yourself, well, if the whole thing's storm, then is any of it storm? Right? And in fact, this is exactly what's happening. You have these little spiral shapes. They're called storms or vortices. You can think of them as hurricanes. And they all move around the pole. And as they move, they push by one each other and they create basically whirlpools, more or less. Okay? So you think, wow, the South Pole is really crazy. That can't possibly be what's in the north. What? What's weird about this one?
Lighter.
It's lighter, good. So the composition's probably different.
It looks like it has less hurricanes.
Maybe less hurricanes. Let me go back for 1 second. Here.
Closer to the sun, so the light is gonna be lighter.
Well, we don't know when in the year these were taken, but that could possibly be. I mean, they're both illuminated, so they both have to be pointed towards the sun. One thing that maybe you don't notice right away, but I thought was really cool. Come on. There's a diamond in the middle. What? Okay, look at this. See this? There's like a cross. What? This is a soft object. Why is there something that looks so symmetrical? So these storms, they're forming like these little eddies and whirlpools, but there's no preferred direction underneath. And there's natural symmetry. And they wind up making perfectly balanced storms across from one another. Okay, so normally when we think of hurricanes, right, they last maybe a couple days, couple weeks. How long do we think these are lasting? Yeah, years or decades. What? That's crazy. Okay. You can call them vortices. That's exactly what we were seeing before. There's certainly some similarities in the color, in the rotational aspect of them. Okay. This one's also really cool. So this is the section of the class that I just think of as like Van Gogh would absolutely enjoy. So what you're seeing here is a real picture, which just doesn't look right. It looks fake. I don't know. I've seen this many, many times. I don't know what to do about it. When you see, we're gonna look at some, I mean, for the most part, it mostly looks flat, right? You get that illusion or no? No, it doesn't look flat to people? Oh, that's good. Okay, my dumb brain makes it look flat to me. But there's actually shadows. And they go in the direction that you think you might be seeing here. So for example, this might be more shaded than this is, if the illumination comes from the bottom left, for example. Which means that there's different heights in the surface itself. I shouldn't say surface, but cloud surface, cloud tops, so to speak. Another great example, I don't know. I feel like you can just put it up here and it's really cool and you should see it. So, yeah, it's a little scary, it's a little spooky, right? You see any like faces in here? The seahorse, yeah, maybe we should just spend a few minutes looking for things. So each of these individual vortices comes from flow in the atmosphere spinning on itself. Why did the flow in the atmosphere spin on itself? Talked about it in the context of hurricanes. Rotation, yeah, the Coriolis force. So here, the Coriolis force is a product of the rotation rate and how large it is. And it turns out for Jupiter, both of these things are very large. So that product is very large. And that's why you have such vigorous storms on Jupiter. Okay, you'll see something similar on Saturn, but nowhere to this extent. And the detail is absolutely beautiful. Okay, so you can see something that's called eddy scaling. This won't be on the exam, you can forget it right away. But let me show you something that happens from the largest storms. We zoom in, you're going to see that there are just storms inside of storms. We said that for the Great Red Spot. And here you can see that as it winds up, it also makes these smaller storms that are winding up material. And this is how energy is getting dissipated in this gas. Okay. There's another one. They're just too cool. Questions about this? Let me show you a couple more and then we'll be done. Okay. You can see, I don't think this is anything close to the Great Red Spot because it's white. And all of these different forms that you'll see. When you see a picture, for example, of Jupiter and the Great Red Spot is in one place, that's true. But in fact, we can make images and we'll see that a lot of the features are changing from orbit to orbit. So for example, you'll see something like this and you might try and hold this in your mind. You'd be like, well, this kind of looks like there's some legs here, like a a lizard, and then there's like a big circle. So circle being thrown by a lizard, and you look for that in the next time, and it'll be totally distorted and you won't be able to recognize it anymore. The banding, see this banding here? Always goes in the direction of the rotation. And that's the only thing that I've sort of kept from you so far. So you can see that here when we go back to look at the picture of the south pole, which is this piece. It's a larger version of that. So the rotation axis is here at the bottom. Material is moving from left to right or right to left, I forget which direction. And you'll see that all of these circles here, they go around the rotation axis. Okay. Okay, so let's watch a fun video. So this is a, oh, come on. Let's do music on today. What you're gonna see here is a composite first of,
Can you go back to the last picture? So I can see it?
yeah. So all of these individual white spheres are water ice clouds. This color is ammonia, and then a combination of those in here. What I'm about to show you is a Juno orbit. And what they did here, they started out really far away from the planet. In fact, they started by Ganymede, by one of Jupiter's moons. And they just add these photos together. And then they have a, what are they called? Graphics team, add the music in so it looks a little bit prettier. So almost everything that I'm about to show you is true, except for one detail. And when we get to the end of the video, I'll explain what that one detail is. I promise it won't ruin anything. And I think they put it to pretty insane music. So let's try this out. Oh, this is the wrong one. Okay. Called a flyby. They speed it up because they don't want you to wait too long. And they're going to turn around. We're going to look at Jupiter. It's going to start by being illuminated from behind and fly onto the daily side. Okay, so there's Jupiter. Let's swing around. You can see it. Those are stars in the background. Those are fake. They're added in afterwards. These are real images. Okay. Yes, there's massive amounts of lightning. Okay, you have water vapor, you have giant cloud systems, and you have heat. And those are what we need to understand that we need more lightning. Now they added that in now. But the rest of the picture. What they've done is they stitched image after image after image off each other. fun? Okay. Hopefully not everyone's asleep. That's fine. So you can play that back. Come on, I don't want this. They were so proud of themselves when they made that. Okay. Come on, what's happening? There we go. Hold on, let me just stop this. I don't know why this isn't stopping. There we go. How close was it?
Yeah, because it's like, I think for me, one of the reasons that's hard to like, feel is the depth perception.
Yeah.
You know what I mean? Like there's no, you know, look at the earth, you can see, like perception of this.
Yes, that's correct.
Close to it.
At different points here, you're multiple Jupiter radii. So what that means is, at the closest point, I think you're about 40% of a Jupiter radii away. The problem is it's really hard to internalize how far a Jupiter radius is. So Jupiter, and we'll talk about the exact dimensions in a little while, it's very big. So this would be like being 40% of the distance above the Earth. So if we put that into context, the Earth is about 6,000 kilometers on the side. 40% of that is a little bit more than 4. No, a little bit more than 2. The 2.5. So it's like 2,000 kilometers away. Let's see if we can do this better. Yeah. Watch. I don't know how many miles that is. Okay. Here's the Earth, or here's Jupiter. It's 40%. It's like this far. That's the closest approach. But its farthest approach is like 10 times. It's like out here. So it's like starting way up here, going really close in, and then going back out. And every time you go really close in, you're changing your orbit slightly. So you get to see a different part of the planet. Okay. Okay. What's this one? Saturn. Everyone knows Saturn. Why? Massive rings. Okay. And how is this a real photo or is it a fake photo? It's a fake. It's real. This one is a real photo. How did they get this picture? It's correct. The sun is on the other side. Okay. And so this is called back illuminated. So it's like you take that picture for your profile that's very artsy. That's this one. Right. Of course, Saturn's a bit of a show off. So Saturn's rings are, of course, the thing that most people are familiar with. Come on. Why is this not working? Okay. These are Saturn's rings from when illuminated from below. They're big. Very big. Anything else you see about that? It has a space. Yeah, there are gaps. How many gaps do you see?
There's a bunch of.
More to like the middle, leaning to the right.
This one? That's a big one. There's this one. And then there's a little tiny bitty one. Right? Okay. What about its atmosphere? Is that anywhere as impressive? Boring, right? Only thing it has going for it is the rings. And we'll come back to how cool these rings are in a little while. We'll talk briefly about the atmosphere itself. What's this again? It's aurora. Is this a real image? Yes, it's a real image. It's 2 images. So it's a visible image, and then they added on top of it the ultraviolet part, which is shown here. Okay. Is this a real image? Why won't this work? No. How do you know? It says in the bottom left, not a real image. Okay, this is an artist's impression of what? The rings. The material in the rings. And in fact, this is the part that is the most flabbergasting to people, is how thin the rings are. It's mostly made of icy material like this, crumbly bits, dust, ice, but they're like that. Okay, this is a real picture. These are the rings seen from the side. And they're not even perfectly edge on. Okay, so I'm showing you three things here. In the background, you're seeing Saturn's largest moon, that's Titan. Come back to that on Thursday when we talk about moons with atmospheres. What? And then you have, I believe this is Enceladus here. What's that little thing? It's a moon, yeah. Yeah, weird. This is not our moon. No, no, no. Our moon is circular. What is this? No. It looks like it might not be circular. And you're like, oh, it just looks distorted. Yeah, it looks a little oval, right? It looks like an egg or something. It's too small to be rounded. And we talked about this when we talked about icy moons. They have to be a certain size before they actually round out. We'll talk about this more when we talk about the icy moons on Thursday. What's that?
Part of the dark part.
Yeah, it's part of the dark part. There's certainly darkness here. And then there's a little thing.
Is that the reflection from the moon?
This is another moon.
Yeah.
You're just calling anything a moon. Yeah.
Like, what makes like a moon and moon and like?
Ooh, very contentious topic. We're gonna come to that when we discuss Pluto. Is that okay? Okay. Because it's a little annoying. Mostly it's about size. So most moons are orbiting something else. Jupiter has a bunch of moons, but they're not all circular, right? But also the moons of Mars weren't circular, so circularity doesn't have to do with the moon, but a planet is almost always circular, right? Okay. Why does this not work? If you look very carefully here, this is a shepherding moon. This is inside of the ring. And you see in this little gap, there's a little tiny dot. Very small moon. They're called moonlets sometimes. And what's it doing? It's pulling on the ring and it's disturbing it. And that leads to, so the ring is being illuminated from the left-hand side here towards this direction. And these are little shadows from pushing up. Like as this moon moves through, it creates a wake, right? Just like you would have a boat moving through water. And that wake behind the moon creates a shadow on the rings. Cool or not cool? Cool. Okay. Questions about this? Right. There is an atmosphere on Saturn, believe it or not. It's just, I don't know why I keep trying. It's just not as interesting. So we do see sometimes these cool storms. This is a new storm that I think started going in 2015. They're short-lived. They're not as intense, and especially here at the surface, they're nowhere as you know, we saw this structure in Jupiter where there's a ton of little circles and everything else. This one kind of looks like maybe something's happening, and it's like smoke on a windy day and blowing behind, right? Doesn't look like there's all that spinning that there was before. Why is it? Who spins faster, Jupiter or Saturn? Jupiter. Who's bigger, Jupiter or Saturn? Jupiter. Jupiter. So when we talked about what causes intense storms, we said it's the product of two things. The spin was really important. And the size. Yeah, both of those together give you the Coriolis force. So both of those are smaller here for Saturn. So we do expect that it'll have slightly less intense storms. Now they're still bigger and crazier than anything we see on Earth, but that's not the point.
I have a
Okay.
question.
Yeah.
The dark part, was it there at one time and then it appeared that way?
Yeah, good question. So I didn't point out one part of this picture. What's this? Shut up, what? Where's the rings? Yeah, Yeah, it's right here, it's edge on. It's tiny, tiny thin. Okay, being illuminated from this direction, so this is the shadow. Okay. Here's the North Pole of Saturn. What is happening here? This one's a hexagon. Why? This is a real picture and it really is hexagonal and it's been like this for decades. This is crazy. Okay, so on the pole, you can see there's the pole right there, little circles all the way around. And then out here, just so happens that the way that this storm works, it ends up being hexagon. Where? That's just I think a problem with the projector, maybe a problem with the image. That's not real. That's not like an alien. Okay, so should we watch another fun video? You've all earned it, right? Okay. I think we're gonna skip forward on this one, but we'll find out.
It's springtime on Saturn, and the hexagon is out. A perfect six-sided hurricane, 60 miles deep, that could swallow 4 Earths. It's ringed by winds of ammonia and hydrogen blowing 220 miles an hour. The storm was seen by the twin Voyager spacecraft when they passed by in the early 80s. That was the last time until recently that sunlight graced the North Pole of Saturn, which takes 30 of our years to make one circuit of the sun. Soon after the Voyagers departed, winter descended. Saturn's rings tipped away from us, plunging the North Pole into 15 years of darkness. Without sunlight, astronomers were limited to infrared images. They showed the hexagon was still there. But what is it? The hexagon is a narrow jet stream that circles the North Pole. Researchers think that friction with the slower clouds on either side of it creates eddies, mini storms that push the jet stream into a wave-like shape as it goes around. By spinning columns of water at different speeds, scientists have been able to reproduce the six-sided pattern in the lab. In January of 2009, the sun began its slow rise in Saturn's north. Summer was coming. The Cassini spacecraft was there to see it. In the coming months, Cassini will slip between Saturn and its rings to pass right over the storm for a closer look. But that's not all there is to see up north. Saturn has an aurora, its own version of the Northern Lights, a ring of electrical fire guided by the planet's magnetic field.
Ultraviolet images.
Rings of ice and a dancing ribbon of aurora sitting smack on top of a six-sided hurricane. Another jewel in the crown of the solar system's most photogenic planet, where the voyage and the discoveries go on.
Pretty cool, right? Okay. Let's skip to this one. Boring ones. Okay. Questions about that last one? Yeah.
So we were talking about like seasons real planet, like what do seasons on like gas planets?
Yeah, it's a very good question. So how would a season on a gas planet present itself? So if this were the axial rotation and you were the sun, then you get the same amount of light everywhere. But if I'm rotated away, then I get more here than I would here. But this is a little complicated because if I'm the Earth, for example, that means that this is warm, the pole here starts to melt, and this one starts to freeze more. But if I don't have a surface, then it's just gas moving around, bumping into other gas and redistributing the heat. So there's no caps that form. there's not really like a major difference in the way that we think about the temperature, except for how it's distributed. Does that make sense? Okay. Okay, so by comparison, these are really boring. So we just talked about Jupiter and Saturn, and those are what we call gas giants. And then annoyingly, we call these ice giants. Anyone know why we call them ice giants?
They're way down, way the highest.
They're like way out where ices are forming that we don't have anywhere else in the solar system. So those ones really are made mostly of hydrogen and helium. We didn't really talk about the composition. We're going to talk about them in a few seconds. I'm going to show you what Uranus and Neptune look like. Want to know how to say it without giggling? That's how you say it. Okay. You can say it the other way too, and that's the mark of being an adult. You don't. I'll just say it. Okay. So which one is cooler? Uranus or Neptune? Neptune. Neptune looks way cooler, right? What do you see on Neptune that you don't see on Uranus? Clouds, yeah. I mean, Uranus looks featureless. Neptune looks like it has bands still. That's correct. So there, in fact, is a giant storm on Neptune. That's called the Great Dark Spot. Really great names, astronomers. And if you look very carefully on Uranus, you'll see that, in fact, there are bands here. But the structure that you're seeing here is not great for your eye. The composition of the clouds here is a lot of methane, nitrogen-based clouds. And so they show up mostly blue. They don't show this like beautiful coloring that ammonia and water ice are having between each other. Okay. So we look with JWST, and there's rings. This is Neptune's rings, by the way. And there's a lot of other fun stuff too here. What's that? You can read it. It's Triton. What is that? Its biggest moon. Yeah. Really cool names, guys. Titan, Triton. That's not going to confuse anyone. So Titan is the largest moon of Saturn, and Triton is the largest moon of Neptune. And you have all of these tiny itsy bitsy moons. Okay. You even have moons like Galatea here that seems to be inside of the ring. So there might be a relationship between how the rings are formed and the presence of these things that are orbited. For example, here's Despina, and it's inside of this interior strong ring. Okay, yeah.
So do all planets with the ring have a moon inside?
Okay, interesting question. So for something like Jupiter, it has very faint rings. And those rings are, in a lot of cases, related to the moon. For Saturn, there are several rings and several moons. And some of those rings are associated to some of those moons, and some of them are unexplained. And in this case, these two that we see are directly correlated to the presence of these things. Does that make sense? Okay. Rings are weird. And we'll talk about more rings. We expect them to be young because stuff that's just floating in space doesn't float forever. Does that make sense why that would be? What happens to say you take a snowflake and you stick it in space? Space hot or cold? What? Cold. Okay, it's cold, and it's, remember, space is the weird one because it's both hot and cold. What? Shut up, Mateo, that doesn't make any sense. Okay, there's no gas. So what we think of as warmth, right? Currently, this is a pretty warm room. Okay, there's nothing to bounce off of your skin. So you would think of that as cold. But if the sun is shining on you, you're getting hit with UV, X-rays, really high energy light. And that's going to heat anything up dramatically. So you're both hot and cold. Does that make sense? So you take a snowflake. Did you say no? Okay, take a snowflake. Okay, you bring it up into space. In a few seconds, the intense ultraviolet light and X-rays will start to break it apart. Now it's a little bit better because you're quite far away. So you have a lot less than you would say at Mercury. But definitely here, if you take a snowflake, bring it up to space, it melts almost immediately, gets destroyed, becomes its constituent atoms of hydrogen and oxygen. Yeah.
What's the purpose of a ring?
Purpose of a ring?
Yeah. It's like some planets can survive without it, they don't have it, and then some do.
Yeah, so this is a really interesting question. I think another way to maybe say this is, why are there rings? Why are there rings? We're gonna go to this on Thursday. Okay. I will tell you that the rings exist because they are being continuously replenished. And there must be a source for the rings. So whether that's a system like Saturn, which means that you have these really beautiful rings, likely came from a recent moon being absolutely annihilated. And that's just the leftovers. Or something like this, where it's very thin, very hard to see, and you have these small little moonlets that are losing atmosphere or losing their surface and going into orbit around the object. Okay. This is another view of that same ring system. Of course, it's close, but you can also see other things here in the infrared. So you can see bands still. Remember, I promised you that Neptune has bands. And one of you pointed out the great dark spot. I don't think you can see it here, but you can see these regions that are really bright. What does brightness mean again in infrared? Hot. So you have these huge hot spots in the surface where material is coming up from below and making its way into the atmosphere. Okay? Yeah.
An explanation why this thing is more oval shaped instead of circular.
What do you mean by that?
Like, I know the regular image of that's shaped like the storm being more oval shaped rather than
Like here?
Yeah, I think that's
No, I don't have a good explanation for that. I can see if there is a consensus. One of the reasons why we want to go back to Uranus, why we want to go back to Neptune, is we can only get this type of information by being there. They're very far away. They don't produce a lot of their own light. So it really helps to be in orbit around them. We have not flown by them except for with the Voyager 1 and 2 spacecraft, which were in the late 70s. It's been a minute. Why does it take so long to get to these places? They're far away. They're really far away, and we don't have the ability to go infinitely fast. So light, can take hours to get there, 8 hours. We're going a fraction of that speed. So it can take like 10 years to get out to the edge of the solar system. So if you want to plan a mission to go to Uranus to study something, you got to do it 10 years ago, right? So when you have a government that decides to do this thing and then this thing and then this thing, they don't fund you for 10 years. You still have to wait another 10 years in order to actually launch and get out there in the first place. Okay. Questions about these pictures before we do the boring learning stuff? Okay. So what the hell are these things made of? Okay, you don't have to write this down. You can find it anywhere. Jupiter. That's this one, biggest one. It's 5.2 AU. That's 5 times as far away from the sun as we are. Its mass is enormous, 320 times the mass of the Earth, but its radius is about 10 times as large. Okay. The density is 1.3 grams per cubic centimeter. For reference, the density of water is about 1. The density of ice is about 0.9. The density of rock is between 3.5 and 5. Sometimes 7 if you're thinking about iron. Okay, so it's mostly made of hydrogen and helium. Weird. Okay, here's Saturn. It's about twice as far. All right, we can round these numbers because we're all friends here. Here's mass. It's almost 100 times the mass of the Earth. But it's almost 10 times. That's weird. That wasn't a very big change. You expect that? No, that was weird. Okay. What about this one here? The density is 0.7. So that's less than the density of ice. Okay. Does everyone understand that ice is less dense than water? Counterintuitively. That's why ice floats. Water doesn't. Okay, cool. I gotta repeat that. Uranus. It's about 20 AU. So this is about 4 times the distance that Jupiter is. And its mass is only about 14 Earth masses. Its radius is about 4. Almost the same as Neptune. So actually, Neptune's a little bit larger in mass. Weird. The densities are kind of different. And you look at this and you say, well, there's water, there's ammonia, and there's methane, and hydrogen and helium. So hydrogen and helium is a primary component, then water, then ammonia, then methane. So this is the composition. Same thing's true here. Weird.
Why, those, the first 3 only have hydrogen and helium, but nothing else?
So actually just the first 2. These 2 are hydrogen and helium, and these 2 have all 4. And that's a very good question. Why do they have this structure? Why are these hydrogen and helium, and why are these containing water? And we're going to talk about this when we talk about the formation of the solar system. But interestingly enough, I will tell you, I won't explain it until we get to this later. Neptune probably used to be here, and Uranus probably used to be here. They swapped places. What? Yes, that's correct. What is the right answer? Okay, let's talk quickly about the density. So we're going to talk about these individual objects, and then we'll talk about how they formed. Okay. So here's Jupiter, Saturn, Uranus, and Neptune. And this is the density as a function of each of these. So 1 is water. They're all really dense. Are they made of rocks? No. They're mostly gas all the way down. And which of these float in water? Saturn. So if you had a giant solar system sized pool, Saturn would float in it. Of course, that's nonsense, but you know what I mean. Okay. Why is Jupiter denser than Saturn?
Fine.
Yeah, it's more massive. The radii are mostly the same. Recall that density is simply the total mass divided by the total volume. If the volumes are roughly the same and the mass is larger, then the density is larger. Okay. Jovian planets, I like to think of this analogy, and actually you can think about this in terms of most atmospheres. Their atmosphere is almost all the way down. Jupiter might be atmosphere all the way to the bottom. Kind of a weird way to think about this. But essentially, if you add gas to the very top, what does it do? It presses down on every layer below it. But since it's not hard, that stuff at the bottom just gets pressed more. Okay, so this is like when you're going to sleep and you have 7 pillows and the one at the bottom inevitably needs fluffing, right? So this bottom one always gets so squished and it's not comfortable, so you have to unfluff it, right? That's because your head is squishing it down, right? Questions? Okay, let me ask this question. Okay, wait. Yeah. Over 2,000 planets have been detected around other stars. So far, we believe most are gas giants, and most are more massive than Jupiter. Should these massive planets be smaller than Jupiter, about the same size as Jupiter but more dense, about the same size as Jupiter but less dense, much bigger than Jupiter? We have no idea of the size because we can't see them directly. Tell me that you're ready to vote with your fists. Let's vote on 3, 2, 1. Interesting. I don't think I see any two people sitting next to each other with the same answer. Want to ask your nearest neighbor just really briefly what their answer is and if they can defend it? Okay, let's re-vote. Show me your hand. Okay, let's see your votes on 3, 2, 1. Okay, interesting. Okay, we got a camp for 2, about the same size as Jupiter, but more dense. We got a camp for 3, about the same size as Jupiter, but less dense. And D, much bigger than Jupiter. No one said smaller than Jupiter. Okay. All right, we're gonna see this in 2 seconds. Adding mass to a Jovian planet compresses it like pillows, but it doesn't make it much bigger, just more dense. So we saw that when we saw Saturn. So for Saturn example, it was about 10 times the radius of the Earth and about 90 times as massive. When we added an additional 210 Earth masses of hydrogen and helium, how much did the radius grow? From about 10 to about 11. And the density went from subwater to slightly above water. Okay? Annoyingly, it looks like this. And if you keep adding mass, something really counterintuitive happens. The radius gets smaller. Yes. So over here you have Jupiter. Here's Saturn, a third of the size, but only slightly smaller. And if you keep going, you keep adding mass, it'll actually make it smaller again. Because now there's so much mass, it's pulling it in really tightly. Okay? And we see this when we look at hot Jupiters. Okay. I already said that. What about Uranus and Neptune? They're kind of weird, right? This is just from the difference in composition. Notice up here that the hydrogen and helium is the primary constituent. In fact, there really isn't much water at all. Here, a significant fraction of them, of the planet, is from water, ammonia, and methane. Can anyone name what, say, water's chemical structure is? H2O, good. H2O. What about ammonia? NH4, okay. Methane? What's that? CH4. So what did I say there? So I said, okay, water was H2O, ammonia is NH3, methane is CH4. Okay, so all of those are oxygen, nitrogen, carbon, and just add on a couple little hydrogens. Hydrogen's okay, right? Hydrogen is what this other stuff is made of. But now I can take heavy things like oxygen, 16 times larger than hydrogen, nitrogen, which is 14 times larger than hydrogen, and carbon, which is 12 times larger than hydrogen, and I can add it in to my planet. So if I can get that stuff, turn it into ice, I can stick it in my planet and make it slightly heavier. And that's why these densities are almost as large, if not larger, than Jupiter's. Okay, so the composition matters here too. Let's see. I already said that. We're not going to say this again. Okay, come on now. So what we're saying here, they have less H and less HE by fraction. Okay, more H compounds, but not a higher percentage of H compounds. Okay. H compounds are those things that we just mentioned. Water is oxygen with hydrogen. Ammonia is hydrogen with nitrogen. And methane is hydrogen with carbon. Hydrocarbon. Okay. You might have heard of ethane. Ethane is another version of a hydrocarbon. How do these objects get their shape? We're really not going to spend a lot of time on this. So here you have rotation. And essentially what this is doing is it's flinging out the exterior. And it's providing a repulsion essentially to gravity. So gravity is pulling it in with these green. And it's being flung out with these pink. And so it ends up giving you this weird bulge shape where it's pulled in more at the tops than it is at the middles. It's called being oblate. So it looks like a little bit of an oval. And the next time you look at a picture of Saturn or a picture of Jupiter, you'll see that. It's not exactly circular. Jupiter and Saturn rotate every 10 hours, essentially. Uranus and Neptune rotate every 15 hours, and it stretches out the planet. Let's look at the composition really quickly. Of course, Jupiter's exterior is warmer. I should say exterior in quotes. The whole atmosphere is warmer as a whole. And as you go deeper, it gets warmer and warmer and warmer. Why would that be? There are gases, yeah. So the densities are going up. Just like as we go up a hill, it gets colder. The reverse is true. If you come down a hill, it gets warmer. So as I get deeper into the atmosphere, the temperature keeps going up and up and up. And you might be saying to yourself, well, where is the heat coming from? It's not coming from the star, from the sun. Okay, we'll see that in a few seconds. These clouds that give it its beautiful color, ammonia, we talked about that. This one that's weird, ammonia hydrosulfide. So just live on Jupiter for some reason, you get ammonium hydrosulfide, and you have water below that. This is the condensation temperature for water. And that happens at a specific temperature. That's why you see that water forms at the same distance here. This is the difference in the color. So for example, this is the altitude above the cloud tops. Imagine that this is where the cloud tops are. You have much deeper clouds. So water is found well below ammonia. So the reason that Saturn is yellow is because Saturn is mostly ammonia clouds. All the water clouds are much deeper. Okay. Methane over here only condenses in these Uranus and Neptune clouds, and it's the primary source of the color that we see, these methane and water ice clouds. So in Neptune, you saw some white streaks. Those are water ice clouds that are peeking through the methane clouds. Let me quickly show you the interior because it doesn't make any sense and it's really annoying. Okay, so you need to think about Jupiter as its own type of thing. It's not something that you can stand on. You land on Jupiter, you fall forever. Okay, what do I mean by that? Let's start at the top here at the cloud tops. You're in a wonderful, you're like one of those Star Wars ships that flies in to distribute Darth Vader to the unsuspecting person. Okay, and you land here thinking that you're going to get Skywalker or whatever. You got bad intel, and you step off thinking that there's some platform. So what happens? You start falling. Okay, at the very beginning, the temperature is balmy, 125 degrees Kelvin. No big deal. Pressure, 1 bar. I can live in a pressure of 1 bar. That's like what we're living in right now. That's the current atmospheric pressure. It's a lot colder. So we're at about 370 degrees Kelvin currently. So it's cold, but that's what the spacesuit is for. No big deal. Okay. But the density at this exterior is quite low. And I start falling. Okay. And I start falling and the temperature keeps going up. And the pressure gets large very quickly. So can I survive 500,000 bars? No. When do, like, say, normal humans get crushed? Guess. Any guess is fine. 100 bars, yeah. So 20 bars, you're having a really bad day. You're probably, your lungs are getting crushed. And that's 20 times the atmospheric pressure. So by the time you get to 500,000 bars, everything that had an air pocket is destroyed. Okay? So if that was your lungs, you're obviously dead. But of course that doesn't matter because it's 2,000 degrees, you're already melted. So let's think, okay, let's say, Darth Vader had the little transponder on to talk to his ship. How's that doing? It's melted and crushed, right? And every circuit in there is absolutely destroyed, and it keeps falling. So this is something called liquid hydrogen, where the pressure is 2 million bars. The temperature is 5,000 degrees Kelvin. What is 5,000 degrees Kelvin? What's that? The surface of the sun is 5,770 degrees Kelvin. Were you surprised to learn that the interior of Jupiter is the same temperature as the surface of the sun? Now, thankfully, the interior here is cooler. It only gets down to 20,000. The interior of the sun is trillions of Kelvin. That's where the light from the sun comes from. And there's no light coming from the interior of Jupiter. As you keep going, you're falling down into something called metallic hydrogen. This is where the hydrogen is pushed so close together, it behaves like copper. So it's a gas, but it can conduct electricity really easily, and it loves doing it. Okay? So there, the density is close to 1. So if you could somehow get down in a little ship that survived, this is where you could float on the surface like a boat. Okay? Does that make sense? It doesn't make any sense. Okay, that's fine. You get down to here, this is 4 times denser than the atmosphere, 4 times denser than water. This is 25 times denser than water. And they did this, which I don't really like, because we don't actually know. There might be nothing down. It might be metallic hydrogen all the way down. We obviously can't go and look, right? So you might be asking yourself, how the hell do they know all of this? If you fly really close, you can feel Jupiter pull on you from different directions, and you can measure that. You send it home, and then people do computer models, and they say, I think I understand what's inside. Okay. On the right-hand side, this is a to scale Earth. And now you understand why this is a really big difference in the 2 planets, right? This is 11 times larger, obviously. So this is us living in this tiny, tiny sliver up here. And now imagine you had 11 Earths of atmosphere crushing you from above, right? So this is why there's not really a surface on Jupiter. It's just gas all the way down. Okay. So it acts like a metal, but it's not solid. At no point can you like step on something. Okay. One question, should Jupiter have a magnetic field? Is it no, the core is solid from all that pressure? B, no, it's not rotating fast enough. C, no, the interior is too cold. D, yes, a moderate magnetic field since the core has 10 times Earth's mass. Or E, yes, a strong magnetic field due to the metallic hydrogen. Show me your fist when you're ready to vote. Let's vote on 3, 2, 1. Yeah, I don't think I tricked very many people. Most people said at least 4 or 5. In fact, it's 5. Metallic hydrogen. What are the things that we need for magnetic field as far as we understand? Rotation, good. Interior heat, it's got to be molten on the interior. That relates to the interior. What was that one? It's convection. Okay, so that we don't have to memorize those, but we'll see them over and over. And it turns out that it has all three of these. So recall that convection is a way to redistribute heat. So it's hot in the middle, it's cold at the top. So hot fluid rises, cools, and then comes back down again. That's the convection part. We already know it's rotating quite rapidly, and it's conductive. Okay, so that conduction allows strong magnetic fields because it's metallic hydrogen. I'm about to show you a picture of that. Here's the shape. Okay, this is an inset here with the true size. That's 200,000 kilometers. That's Jupiter. And that inset is this piece here. You look in the bottom right-hand side, this is Earth's magnetosphere for comparison, but that's also blown up by a factor of 10. Okay, so if you look in the night sky and you could somehow see in the radio waves, which is like where particles can interact with these objects, Jupiter would be the largest thing in the sky by a huge margin. Okay, so this is the magnetic rotation axis, only slightly misaligned from the magnetic axis, and the axis of rotation only slightly misaligned. On the left-hand side, material is basically, this is moving through the solar system, smashing into the solar wind, and it's bending it around. And it creates this beautiful teardrop shape. Okay, here's the paltry little Earth ones, 10 times as big.
Yeah, the video.
I'll get one. That's a good thing. I'll try and find this because yeah, I mean they're hard to visualize because they're not really bright. Okay, I'll try that. So this is another example. These are all of the magnetospheres. Jupiter's is the largest. In fact, all of them have one. This is Jupiter's 2 scale. And you can see this is the material coming from the sun, bending around like it's a ship, plowing through the solar wind. Saturn's tilted in a funny way. You saw that because it has seasons. We talked about the fact that there was spring occurring in the north hemisphere. Here's the size of the sun, 2 scale. So this magnetosphere is larger than the size of the sun. Now it's okay, right? Because it's not actually putting out the intensity that the sun is. You look down here, there's Uranus, Neptune, WIMPs, right? Boring. We won't even talk about that. Okay. Any questions, comments, concerns? Okay, if you have not turned in your exam, please do so right now. I hope you wrote your name and your student ID number on them. Okay, thank you.